Hi, I'm Ben. I've taught Rust to hundreds of engineers and now I'm putting that experience into this video series. In the previous free video, number 4, I showed you how a struct can encapsulate a resource. And at the end of that one, I said, we are making our way through the Rust type system. The next free video will be about enums, which form an absolutely crucial part of the language. If you haven't yet worked in a language with this kind of support for tagged unions, I reckon after this one you'll be wondering how you ever managed without them. So here we are. Today we're doing enums, and it's time for me to back that one up with something convincing. To do that, I want to start with a little design question for you. We need a type that identifies a host. In this scenario, a host can be identified by an IPv4 address or an IPv6 address or a hostname string. We already have types for each of those. IPv4 address, IPv6 address, and string are all structs provided by the standard library. Any instance of our host type needs to contain exactly one of these fields, and it needs to be completely type-safe to use. It needs to own its data so I can return a host from a function. And if I have a function that takes a host parameter, I need a way to find out whether it contains an IPv4 or an IPv6 or a name, and then get out a variable with the correct type in each case. There has to be zero possibility of type confusion. The problem we're dealing with here is called polymorphism, and it comes up all the time. Polymorphism just means many shapes. We need a single type, host, that can take on 3 different shapes, an IPv4 or an IPv6 or a string. I'll give you a moment to think about how you'd design this type. Rust guarantees complete type safety, so we need a solution to this that is absolutely solid, and that's what we get with enums. Curious? Oh, and one more thing, you're not allowed to use heap allocation. Okay, hands up if you had this diagram in your head. Probably right up to the moment I said no heap allocation, right? Object-oriented programming has trained us to think like this as soon as polymorphism comes up. Obviously, we need a host to be an abstract base class or an interface, and the different host types inherit from that base class or they implement the interface. Then we need a way to test if we can downcast from the base class to each of the concrete types. You can make that work, but the different host types have different sizes, so as soon as you need to return a host from a function, you need some kind of dynamic allocation on the heap. Depending on what language you're in, that allocation might be hidden from you behind the scenes, but it's there unless the optimizer is getting pretty fancy. If you're a C programmer, when I said no heap allocation, you probably thought, okay, fine, I'll make a tagged union. A tagged union has a tag field and a data field. The tag is typically an enum, and its job is to remember what kind of data we're holding in the data field. This is valid Rust syntax for an enum. It's also exactly what you'd write in C, and it has the same meaning. So we're declaring a type called hostKind that can have 3 possible values, and those values are constants called IPv4, IPv6, and name. These are called the variants of this enum type. We use this type as the tag field to keep track of what we're holding in the data field. The data field is a union, and this is a type you may not have come across. This is valid Rust syntax for a union. It works just like a union in C, and the syntax is almost the same. A union is like a struct, except all the fields are shoved in on top of each other. So if you write to one field, you're actually overwriting all the others too, because they all overlap in the same storage space. You can only actually store one of the fields at a time, and you need some data somewhere else to remember which field is valid. That's what the tag is for. The size of a union is the size of its largest field, and when you're storing one of the smaller fields, there's just some padding bytes left over that aren't being used right now. So that's what a tagged union is. It's a tag next to a union that can store one of several data types. You can build this in C or in Rust, and it works great. It's compact, it doesn't need any pointers or heap allocation because it stores the data inline right next to the tag. The only problem is this is extremely not type safe. You have to be very careful that the type you read out of a union is the most recent type that was written into it. For example, if you put in an IPv6 address and then read it out as a string, then you have a string object that thinks it's pointing to a heap allocation, but it could be pointing literally anywhere. It's just whatever bytes came from the IP address. This is definitely undefined behavior, and if an attacker controls the IP address, they can probably use this to hijack the process. For this reason, in safe Rust, a union is a write-only type. It's safe to write to a union, but reading a field out of a union is an unsafe operation. You have to use the unsafe keyword to do it. And there are some restrictions on what field types you can have in a union because of destructors. There's a wrapper called manually drop, but let's not get into that. The point is that if you were to build this tagged union by hand, you'd have to use unsafe code. You'd have to be very careful that the tag always matches the type in the union, and that you always check the tag before reading from a field. And you might be thinking, well, just be careful. We don't use tagged unions that often, just make sure that bit of code is audited and it's correct. The thing is, Rust guarantees complete type safety and memory safety. And once you see how easy it is to safely make and use tagged unions in Rust, you're going to use them all the time. Like, you're going to use a tagged union to represent the result of every operation that could possibly fail. All your error handling logic is going to be made this way. So, finally, here is how we'd actually make this type in Rust. Host is an enum with 3 variants, IPv4, IPv6, and name. But this time, each variant contains the data associated with that variant. So if the variant is IPv4, it contains an IPv4 address, and so on. Under the hood, the representation of this enum is a tagged union, just like we saw a minute ago. But the language is enforcing the association between the tag and the data, so it's type safe. The only way to construct a value of an enum is to name the variant and provide a value of the correct type for the associated data. So to construct the IPv4 variant, I go into the host namespace, I name the IPv4 variant, and I have to provide an IPv4 address for the field. To construct the host name variant, I have to provide a string. Either way, what I get back is a value of type host, which I can return from the function. To access the value of an enum, it's the same thing, but in reverse. The only way of getting at the associated data is by first checking the value is a particular variant. You might remember the match expression from video number 2, where we were matching on character values. We haven't used it much since then, but now that we have enums, we'll be using match a lot more. So we have a function that takes a host, and we feed it into a match expression. Each of these lines is a match arm with a pattern on the left of the arrow and an expression on the right. We go from top to bottom through the list until we find a pattern that matches the value. And each of these patterns binds a variable to the associated data inside the variant. So if it's the IPv4 variant, we get a new variable called IPv4 that is only in scope for the expression on the right of the arrow. That variable is an IPv4 address, so we can pass it to connect IPv4. This is completely type safe because the only way to make a variable that gets at the associated data is with a pattern that matches a particular variant. Match is an expression, and it returns the value of whichever match arm got executed. This function returns a string. If the host contains either an IPv4 or an IPv6, then it calls toString and returns that. If it contains a name, then it just returns the name. And notice here that this function takes host by value. We are matching on host by value, and the variable name in the pattern is assigned the string by value. String is not copyable, so this is a move. Name takes ownership of the string that gets moved out of the enum. That means we no longer have a host object. It's been consumed. It was destructured by this pattern. So the variable name now owns the string, and we can return it to the caller. The match expression needs something to return in all cases, so the list of patterns must be exhaustive. Every possible input value must match at least one pattern. If we miss the IPv6 case, then we get error, non-exhaustive patterns, host IPv6 not covered. Sometimes you might only be interested in which variant an enum is holding, and you don't need to access the associated data. In that case, you can write the underscore, the wildcard, to ignore the field at that point in the pattern. This match expression takes host by value, but it doesn't consume the host because it doesn't bind any variables that would move data out of it. So we can continue to use host after this expression. So now you're probably thinking, wait, what if I want to access the associated data, but I don't want to move the data out and consume the enum? I just want a reference to the data. Well, by default, when you match on a value, any variables in the pattern are assigned by value. But you can change that using the ref keyword. So in this example, I want isLocalHost to be true if the host is a local loopback address. And I'm matching on host by value, so the first pattern binds IPv4 by value, and that's fine because an IPv4 address is copyable. So this just takes a copy of the data. Same thing for IPv6. But when we come to the pattern for name, I'm using ref name to bind a reference. So now the variable name is a shared reference to the string, and I can compare it with the string localhost without moving anything. This is handy occasionally, and I wanted to show it to you so that you know the keyword exists, but there's a simpler way to do this that you'll often end up using without even really thinking about it. This time I've removed the ref keyword, and instead I've put an ampersand in front of the host value that we're matching on. So now, because we're matching on a reference, these patterns will bind variables to the associated data by reference. So the variables IPv4, IPv6, and name are all shared references. One place where this happens most naturally is when you're writing a method on an enum. Just like with structs, you can add methods to enums with an impl block. So I say impl host and write the method isLocalHost, which takes self as a shared reference. Then when I match on self, because self is a shared reference to a host, these patterns automatically bind the variables as shared references to the associated data, and this just works. Similarly, I can have a method that takes ampersand mute self. So now self is a mutable reference to the host. And this pattern now binds the variable name as a mutable reference to the string. So I can call name.pushString, which mutates the string in place inside the enum. Let's go back to the type definition. Right now, host is a move-only type. Like structs, enums are move-only by default, and they can opt in to the copy and clone traits. It might be useful if we could make copies of this host type. It's kind of just plain old data, but it does contain a string. Strings can't be implicitly copied, so this type is not eligible for the copy trait, but we can at least derive clone on it, so users can explicitly make deep copies with the clone method. If you're at all fuzzy on the distinction between copy and clone, check out video number 4, Structs and Resources. In that video, we ended up with 3 categories of structs. Types that can be copied implicitly just by copying the bytes in the struct, types that can be cloned explicitly, maybe by doing some kind of deep copy, and types that can only be moved, not copied, because they hold some kind of resource. The same thing applies to enums. Our host type might contain a string which can't be implicitly copied, but it can be explicitly cloned. So it's in this middle category. It implements clone, but not copy. Later we'll see enums that can be copied and enums that are move-only because they carry resources. Okay, there's more syntax that we need to cover, but before we do that, I want to make sure we're clear on the concept of enums and why they're so important. I started by asking you to design a type that could contain one of 3 different types. And importantly, I made one of those types be a string with a heap allocation. If I didn't do that, if we just had either an IPv4 or an IPv6 address, you might have been tempted to say, well, you could just return a tuple or a struct that contains an IPv4 and an IPv6 address, along with a flag that says which one to look at. And whichever field is unused, you could just fill it with zeros or whatever. In languages that don't have native support for tagged unions, this is the constant temptation, and we do stuff like that all the time. For example, in Go, the standard pattern for a function that can fail is to return the desired result along with an error. So here's a function that opens a file, and it returns a file and an error. This return type looks like a tuple. Technically, it's not actually a tuple, it's just a function with multiple return values. But the point is that when you call it, what you get back is a file pointer and an error. So we call the function, and now we have two variables, one that might contain a file and one that might contain an error. And you're supposed to check if the error is nil before using the file. Now we expect that either the file or the error will be nil. It would be weird if both the file and the error are nil, and it would also be weird if they're both non-nil. Logically, those would be invalid states, but the return type allows them. Those are invalid states that can exist in this type signature. This violates an important software design principle: make invalid states unrepresentable. The benefit of this principle is that it gives us the most possible assurance from the type system. We'd prefer to find our bugs at compile time rather than at runtime. Now you might say, okay, but this open function is in the standard library, surely we can rely on that. And everyone knows that when you have a function that returns an error, you're supposed to check that it's nil. Okay, great, but these are the same language facilities we use to write our own libraries, our own APIs. So let's say I have a function that reads a config file from a standard location and parses it into a config object. So I do the standard thing. I call readConfig, I get back a config and an error. I check the error is nil before I continue. And now I assume that config is not nil and I start using it. But what if there's a comment I didn't notice that says, if there's no config file, this just returns nil for both the config object and the error? I do all my testing with a config file, it seems fine, we ship, and then someone runs it without a config file and it crashes with a nil pointer exception. This becomes an error at runtime that I really would have preferred to catch at compile time, but the knowledge about which states are valid is contained in a comment, and the compiler can't check those. With types like enums, we can clearly articulate which states are possible. We get a lot more confidence that we're not going to run into problems like this at runtime. By the way, I know it looks like I'm picking on Go here, and Go's error handling is a pretty popular punching bag, but really I could use just about any language to illustrate this problem. It's only a handful of languages that have really good support for tagged unions. So, what would this example look like in Rust? Well, we could build it like this. The real open function is a bit more flexible because it uses some generic types. This is just a sketch to keep it simple for now. We'll get to generics properly in a future video. But this is enough to make the point that the open function returns an enum, and there are only two possibilities. Either open succeeds and we get back a file, or open fails and you get back an error. There's no such thing as nil here, so if you get the OK variant, you definitely have a valid file object. Or if you get the error variant, you definitely have a valid error object. And by the way, file is a move-only type. It represents a resource, and this file result type might contain a file, so file result must also be move-only. It can't be copied or cloned. What about our function to read a config? This time it's explicit that there are three possibilities. None means there is no config. OK means we got a config and here it is, and error means there was an error. The only way to start using the config object is to first check that we got the OK variant. Now, we don't actually have to invent a new enum type for every function that can fail. You probably already know, or you've guessed, that Rust has generic types for these situations. They're called option and result. And if you go to rustcurious.com, you'll find them on this map of the type system that I call the elements of Rust. When you're writing any software that matters, error handling is a really important topic. Rust has some very concise syntax for handling errors, and it pulls together enums, generics, and traits. There will be a video going into detail on that, but first we need to finish covering the foundations of the type system. So, stay tuned, we'll get there. We've been talking about these enums as tagged unions. Sometimes they also get referred to as discriminated unions or sum types. I want to explain that last term because I think it helps with understanding. It's called a sum type because the total number of possible values for an enum is the sum of the number of values for each variant. You know that a U8 is a byte, it's an 8-bit value, so there are 256 different possible values. So how many possible values are there for this type? Well, the variant called null only has one value, null. The variant bool contains a bool, so it has two values, false and true. The variant byte contains a U8 with 256 different values. The total number of different values for this enum is just the sum, 259. That's why enums or tagged unions are sometimes called sum types. Contrast that with a struct. This one has two fields, a bool and a U8. How many different values can it hold? Well, the bool has two values, false and true, and for each of those the U8 can take on 256 different values. So to get the total we have to multiply for a total of 512 different possible values. That's why sometimes a struct is called a product type. A type system that has sum types and product types is sometimes described as having algebraic data types. To make a new type, you can add sets of values together or you can multiply sets of values, and that counts as having an algebra over the types in your language. Anyway, it's just a fancy way of saying you have structs and enums. Graydon described it to me as like having electricity and running water. Once you get used to having enums with associated data, they become essential. You just can't go back. We started this video by talking about polymorphism, types that can take on several different shapes. Enums give us closed polymorphism, meaning the enum defines a closed set, the entire set of variants that are allowed for this type. Rust does also support open polymorphism, where you have an interface that can be implemented by multiple types, and new types can turn up and implement that same interface. This is the kind of polymorphism we're more familiar with from other languages. In Rust, interfaces are defined by traits. We can use traits in a way that's resolved at compile time with generics, or we can use them with something called trait objects that gives us dynamic dispatch at runtime. There'll be a video soon about generics and traits. It's a big topic. Coming back to enums. This is the event type from a crate called crossterm. It's a cross-platform library for making interactive programs that run in the terminal. And we have variants for each of the things a program might need to respond to. Input focus, key events, mouse events, pasting from the clipboard, and resizing the terminal. When an enum type is public, which this one is, then its variants and their fields are also public. The variants and fields inherit their visibility from the type. This is different from structs, where the fields are private by default. If you want the variants and fields of an enum to be private, you'll need to hide it in a private field inside a struct. So when you use an enum in a public API, the set of variants is visible to the clients of that API. If you write a program using crossterm, you'll have some code like this, where you receive an event, match on it, and handle each possibility. And like we said earlier, matching must be exhaustive. You have to handle every possible value of this enum. This means that if one day the developer of crossterm needs to add a new variant to the enum to represent a new kind of event, that will be a breaking change to the API. Like, let's say there's a new event called suspend to tell the application it's being put in the background. I don't know, I just made that up. But now the existing match expression will hit a compile error complaining that it doesn't handle that new variant. And that's fine, it's okay to have a breaking API change. Cargo packages have proper support for semantic versioning. You just bump the major version number and downstream users can deal with it. But if you'd prefer to be able to add variants to an enum in the future without it causing a breaking API change, there's a way to do that. The non-exhaustive attribute means it's not possible to exhaustively match on this enum. So even if you list all the currently known variants in your match expression, the compiler will complain that you still need to add a wildcard pattern with fallback handling for any variants that are added in future versions. So in our handle event function, we have to add the underscore, which is the wildcard pattern that will match anything. An example of the non-exhaustive attribute in use is the error kind enum in the standard library. Like the documentation says, this list is intended to grow over time. And just to be clear, this attribute doesn't change anything about the representation of the enum. It's still closed polymorphism. It just means any client code matching on this type has to include a fallback wildcard, so it will still compile in the future even if a new variant is added. Finally, it's time to show you the rest of the syntax that can be used with enums. This enum represents a shape that can be a dot, a circle, or a rectangle. And now we see the three syntax forms that are allowed for variants. These look just like the three forms of structs. To be clear, variants are not structs. They are not distinct types, and the layout in memory is probably different from a struct because we need some space for the tag. The compiler is allowed to optimize the layout around that, but in terms of syntax, they look like structs. So, dot is a unit-like variant with just a single value and no fields. Circle is a tuple-like variant. This one just has a single field for the radius, but you can have a comma-separated list of fields just like a tuple. And rect is a struct-like variant with curly braces and named fields for the width and height. I could have made this another tuple-like variant, but I wanted to show you an example with named fields. This shape type is definitely just plain old data, and all the fields are copyable, so let's derive copy and clone. And that completes our bingo card. We have enums that can be implicitly copied, enums that can only be explicitly cloned, and enums that are move only. As we saw earlier, we can write an impl block to add methods to our enum type. Here's a method to calculate the area of a shape. It's read-only, so it takes self as a shared reference, and it returns an F64. We match on self, and for each of the possible variants, we can bind variables to the fields and calculate the area. So if it's a circle, we bind a variable to the radius and return pi r squared. If it's a rectangle, we return width times height. And yes, we're matching on self, which is a shared reference, so R, W, and H are shared references to F64s. Here's another method that mutates the fields in place. It takes ampersand mute self, so now we're matching on a mutable reference, and R, W, and H are mutable references to F64s. When I say star R times equals factor, I'm dereferencing R to get at the F64 and multiplying it by factor. Same thing for W and H. So this scales the dimensions of the circle or the rect by factor in place. To construct a value of an enum, you go into the namespace of the type, you give the name of the variant you want, and you provide values for any fields, just like constructing a struct. So A, B, and C are all of type shape, and we can call methods on them. We've seen match expressions that let us match on an enum and handle all the variants. Sometimes we're only interested in a single variant. What happens if I assume the shape is a circle and I want to get its radius? Well, of course, the shape might not be a circle, so I get an error. Refutable pattern in local binding. When we were destructuring tuples and structs, the pattern would always match the value, so those patterns were irrefutable. A pattern that only matches one of several possible variants of an enum is called a refutable pattern. It might not match, so we can't use it here in an unconditional assignment. So we could use a match expression. This match does nothing unless the shape is a circle. This works, but it's pretty verbose. The println ends up being 2 levels of indentation in, and we have to write this wildcard pattern that does nothing. If we only need to test a single pattern, we can instead use this if-let syntax. If let shape circle r equals shape. And if this test succeeds, the variable r is in scope in the conditional block, and we can print it out. The println is now indented 1 less level. And you can combine this with an else block if you want. What if I have lots more lines of code that need the associated data I got out of that one variant of the enum? What if I don't want all those lines to be indented? Well, I could do it like this. I'm using the if-let-else as an expression and assigning the result to the variable r at the top level. If the shape is a circle, then the result is r2 from the pattern, which gets assigned to r. I've given it a different name so it's clear what's going on. If it's not a circle, we print not a circle and return early from the function. Now we have r in scope for the rest of the function, and we've saved the indentation, but pretty ugly. Instead, we can write it like this. This is called let-else syntax. I can write a let statement at the top level with a refutable pattern as long as I provide an else block. The else block must diverge, meaning execution cannot reach the end of the else block. I can return from the function, I can exit the process, I can panic. If this was inside a loop, I could break or continue the loop. I just cannot let execution reach that closing curly brace because this is an unconditional assignment to the variable r and it needs a value. And notice the semicolon here to terminate the let statement. This way I can have the variable r that comes directly from the refutable pattern, and I can keep it in scope for the rest of the function. This is especially handy if you have multiple enums that you need to handle like this. It's a lot better than nesting a new level of indentation for each one. This let-else syntax is good for error handling, but there's an even more concise form involving a question mark operator specifically for handling errors. That's a topic for a future video once we've covered generics and traits. So we've seen how a refutable pattern can be used as a condition with if-let and let-else. How about using a refutable pattern as a loop condition? This syntax is called while-let. So this time we sit in a loop calling getNextShape, and we'll keep looping for as long as it gives us circles. When would you use something like this? I've been trying to keep this video just about enums and leave generics as a separate topic, but there is one generic enum type we just have to mention, and that's option. Option represents a value that you may or may not have. Option is generic over some type t, and it has two variants. You either have none or you have some with a value of type t. Option is used all the time. So for example, let's say you have a stream of events and you call next event to get the next one. This function needs a way to communicate when you've reached the end of the stream, and it does that by returning an option. So this while-let loop will continue iterating for as long as it gets some event each time. And then when it reaches the end, it gets none, and we exit the loop. Iterators are based on this pattern, and in fact for loops are syntax sugar for exactly this. There's a whole video coming on iterators. We'll get there. I want to give you an example that I hope will help you think about how to design with enums. We started out by introducing enums with this example where we identify a host with an IPv4 address, an IPv6 address, or a hostname string. Well, in fact, the standard library already has a type representing an IP address that could be v4 or v6. So we can simplify our host enum, so now it either holds an IP address or a string. Once upon a time, I worked on software for encrypting network traffic. It was an implementation of IPsec, so it was encryption at the IP packet layer, and it handled IPv4 and IPv6. The flow of packets from any given source IP address to a particular destination IP address would be encrypted with a unique key. And any communication between two IP addresses has to be either from IPv4 to IPv4 or from IPv6 to IPv6. There's no such thing as sending packets from an IPv4 address to an IPv6 address or vice versa. So I started out with a design that carried around the source and destination addresses as separate fields. So I had a function, something like this, that took a source address and a destination address, and each of them could either be IPv4 or IPv6. And now you can perhaps see the problem. We have a design principle that says make invalid states unrepresentable, but this function accepts a state where the source address is IPv4 and the destination address is IPv6. This can be handled at runtime, so I can put the source and destination addresses together in a tuple, so I can match on both of them at once. So now I can write a pattern that matches two IPv4 addresses and another pattern that matches two IPv6 addresses. And that's a useful trick, by the way. You might want to keep that one in mind. It might even be handy for the practice exercise at the end of this video. The problem is, to make this match exhaustive, I still have to handle the possibility of mismatched IP addresses, a v4 with a v6. So I write a wildcard pattern that just panics. This panic should never happen because these addresses come from the header of a packet that needs to be encrypted, and there's no such thing as a packet that mixes an IPv4 source with an IPv6 destination. But right now we haven't represented that fact in the type system. We just have these two IP addresses and they might be mismatched. So how do we fix this? How do we change our representation to make this invalid state unrepresentable? There are only two valid states, a pair of IPv4 addresses or a pair of IPv6 addresses. So let's represent that fact in a single enum with two variants. Let's call it IP pair. Either I have the v4 variant with a pair of IPv4 addresses, or I have the v6 variant with a pair of IPv6 addresses. See how this makes the invalid states unrepresentable? Now the encrypt function takes this IP pair type. We match on it, we get the source and destination addresses, and we call the appropriate function. This is exhaustive, there are no invalid states left over. This change in design eliminated a code path with a potential panic, so that's one less thing to worry about. Before we wrap up, I want to come back to this host type. Previously we had separate variants for IPv4 and IPv6, but now we know the standard library provides an enum for an IP address that can hold v4 or v6. So let's simplify host. Now it just has two variants. It's either IP containing an IP address or name containing a string. So now host is an enum with a variant that contains another enum. What if I want a method on host that returns true if it contains an IPv4 address? Well, I could write it like this. We match on the host, self, and if it contains an IP, then we write a nested match expression to find out if it's the v4 variant. But we don't actually need to write nested match expressions. We can instead write nested patterns. Anywhere in a pattern that you can bind a variable, you can instead write another pattern. So instead of binding the variable IP and then matching on it, we can instead write the pattern with the v4 variant right there. This is another handy trick that you might keep in mind for the practice exercise. Speaking of which, check this out. This is from YouTube Analytics. It's the audience retention data from the video on structs. And I assume it's normal for half the audience to click away as soon as they realize it's just a video of some guy talking, especially about code, especially with an Australian accent. And it's understandable. After about 5 minutes, a lot of people have exhausted their attention span and they need to go watch some shorts to recover. But here's what gets me. 41 minutes in, and what is it that suddenly causes half the remaining audience to tap out? Oh shit, you want me to engage my brain and type some code? Yeah, nah, I'm out. And look, it's fine. If you're just watching because this stuff is interesting, that's great. You're very welcome here. But if you actually want to learn, I cannot stress enough the importance of spending a few minutes in front of a keyboard not quite knowing what to type. I see it over and over in classroom training. The coding exercises are where people actually learn. I've made this as easy as possible. Just go to rustcurious.com/6 and press the button to open the exercise code in the playground. And that's right, this exercise is about the game of Uno. Everybody knows Uno, right? In Uno, we have cards in 4 different colors and we have wildcards. So first we have an enum called color with the 4 different colors, red, yellow, green, and blue. Nothing fancy about the enum itself, but check out the list of traits we derive on this type. It's a plain old value type, so we make it copyable by deriving copy and clone. But we also derive partial equal and equal. These traits represent the ability to compare values for equality. So if I have 2 variables of type color, I can test if color 1 is equal to color 2, and I can test if color 1 is not equal to color 2. Why are there 2 traits? What does partial equality mean? Some values are more equal than others? Well, some types have values that do not equal themselves. In other words, comparison is not reflexive. For example, the floating point types have nan values to represent a value that is not a number, and nan is not equal to nan. So floats implement partial equal, but not the full reflexive equal trait. Anyway, we don't have that problem with our color type, so we might as well derive both. Next we have an enum to represent the symbol on a card. The symbol can be a number, in which case we're using a U8 to store the number. Or it can be skip, reverse, or draw 2. I'm not using wildcards here, we'll get to those in a second. And again, I'm deriving copy, clone, partial equal, and equal, so symbols can be copied around and compared for equality. And finally we come to the type for a complete card. There are two variants. A regular card has a color and a symbol. A wild card just has a bool that says whether or not it's a draw 4. And again, we derive the traits so that cards can be copied and compared for equality. Okay, that's all provided for you. Now we come to the exercise. There are two methods for you to implement. At the end of a game, everyone left holding cards works out their score by adding up the point values of their cards. So this value method returns the point value of this card. And the rules are simple, they're in this comment. If it's a card with a number on it, then the value is just that number. If it's a skip, reverse, or draw 2, then it's worth 20 points, and the wild cards are worth 50 points, whether or not it's a draw 4. So you probably want to remove this to-do macro and replace it with an expression that matches on self and returns the appropriate value. This is the easy one, and once you get this one right, one of the unit tests will start passing. I recommend you make this one work before moving on to the other method. During a game of Uno, you have some cards in your hand, there's a discard pile on the table, and you can see the top card that was most recently played, and there is a current color of play. Usually the current color is just the color of the card on top of the discard pile, but if that was a wild card, then the person who plays it says what the new color of play is. There are rules that determine whether a particular card can be played given the card on top of the discard pile and the current color of play. So this method is called canPlay, and it's going to return true if this card could be played. And the rules are simple. If the card has the same symbol as the card on the discard pile, then it can be played. So a 5 can be played on top of a 5, a skip can be played on top of a skip. And gee, it might come in handy that symbols can be compared for equality. If the card has the same color as the current color of play, then it can be played regardless of the symbol. And finally, wild and wild draw 4 cards can always be played. That's it, those are the rules. So this method should return true if this card is allowed to be played, given the current color of play and the card on the discard pile. Once you get that right, the second unit test will pass. And that's the whole exercise, just write these two methods so the unit tests pass. And you can do that however you want. You can write nested match expressions if you like. Then for bonus points, once you've got them working, if you do have nested match expressions, you might like to go back and see if you can write each function with a single match expression. I dropped some hints earlier on how to do that. The point of this exercise is to give you some practice working with enums. You'll be using them all the time in real Rust code, so it's worth taking the time to get comfortable with them. We've been working our way through the Rust type system. Video number 4 covered tuples and structs, and now you've seen enums and unions. The next video will be about arrays, which means we will have ticked off all the compound types. That video will also cover slices, which sit at the intersection between arrays and borrowed references. Arrays and slices really open up the possibilities for what you can build with the parts of the language we've covered so far, so don't miss that one. You might like to hit the notification bell, or if you create an account at rustcurious.com, then you'll get an email when I publish. Okay, that's it. I hope you're enjoying these videos. Stay curious, and I'll see you soon.